Hi, everybody. In the third lesson here in Unit 1A on atomic structure and nuclear chemistry, we're going to be talking about the effects of radiation and also some practical applications of nuclear chemistry. So if you get a little bit of radiation exposure, the effects might not be apparent for a long time, so you may not really know if you have done harm, especially, if it's a growing cancer or some kind of somatic mutation that just takes a few years to show up. But in general, effects of radiation can fit into one of two major categories. Either they can be somatic. If we're talking about somatic damage, we're talking about basically it occurs in non-germline tissues. What this means is tissues that are not involved in reproduction. So somatic damage is only going to affect the individual. This might come in the form of, some sort of tumor or a mutation or cancer or something like that. Genetic damage, on the other hand, is going to affect reproductive tissues. It's going to affect the DNA in egg and sperm cells. And because of that, it is heritable. That means it could be passed on to children. So when we're talking genetic damage, this can affect children of the person who was exposed. So let's say, mom or dad gets some radiation exposure, and then the kid ends up with some sort of birth defect or something like that because there was some genetic damage there, okay? There's also more immediate effects for really intense short-term exposure that we'll discuss a little bit here as well, okay? All right, now if you want to really look at, what about the radiation is really going to affect the damage that's done to whatever living organism that you're talking about. One is the energy of the radiation, okay? And when you're talking about the different kinds of radiation, again, this is alpha and beta and gamma radiation. Gamma radiation tends to have the most energy, and that can cause chemical reactions to happen in the body that are not supposed to happen. It can damage DNA and all that kind of stuff. Penetrating ability of the radiation. How well does the radiation go through solid objects? How well does the radiation go through the body? So, if it can only affect the surface and is stopped by the skin, then that may not be as dangerous as, say, some radiation that can penetrate deeper. The ionizing ability of the radiation. Now, I know this far in the course we haven't talked a whole lot about ions, but basically, when we're talking about the ionizing ability of the radiation, we're talking about the ability of the radiation to make charged particles. And some charged particles may, again, kind of like the energy of the radiation, can cause some chemical reactions that can happen in living organisms that would be unnatural. And so that can cause it to be more dangerous. And obviously, the number one thing here is the time and the intensity of the exposure. If you're only exposed to a little bit of radiation, that might not be a big deal. But if you're exposed to a lot, then that'll be obviously more dangerous. Also, if the intensity of the radiation is higher, in other words, more radioactive energy or more radioactive particles are hitting the living organism, then that's going to be more dangerous. Finally, the age of the organism. You would think, that younger people would tend to bounce back better, but actually radiation exposure is more dangerous for younger people because one of the major risks associated with radiation exposure is cancer. And if you have a younger person, you're going to have more time for those cancers to develop. as the person gets older. So if you've got radiation exposure on an 80-year-old man, he may die of other natural causes before the radiation causes too many problems. But if you have a young child and they get radiation exposure that causes cancer, then that cancer is going to have a lot more time to grow. And so that's going to make it a lot more dangerous for younger people. So when radiation hits a living cell, one of three main things can happen. Either, best case scenario, the cell repairs itself, or maybe the radiation exposure is too much. The next scenario would be the cell just dies, which quite honestly is not the worst case scenario. The worst case scenario would be if the cell is damaged and begins to grow in an unnatural way. DNA has some information in it that tells basically cells when to stop dividing and when to stop growing. If we're talking about your liver, there is DNA or information coded in your DNA that basically tells your liver cells when to stop dividing and growing and getting bigger, or at least to slow down the growth at some point. And if that off switch that's embedded in your DNA gets damaged, then a lot of times cells tend to grow unchecked or grow unnaturally. So now we're talking tumors, now we're talking cancerous growth. Okay, so scenario one is the best scenario. Scenario two is probably not as good, but a little not as bad as scenario three. Scenario three, where the cell is starting to cause cancerous growth, is the worst. This is a really good video from the CDC that kind of lays that out there for you. I'll be showing that in class. So if you start looking at the penetrating ability of radiation, and our three major types of radiation, of course, our alpha, our beta, and our gamma radiation. This picture kind of shows how well alpha, beta, and gamma radiation could, say, go through living tissue. Alpha radiation doesn't penetrate very well at all. In fact, your skin can stop most alpha radiation. Some may be able to get through, but alpha particles, you'll remember, these are these helium nuclei with a mass of 4 and an atomic number of 2, compared to beta radiation, which has no mass, and again, gamma radiation also has no mass. And so if you start looking at these three different kinds of particles, this particle is humongous compared to these other particles. And so this big whopping particle can't go through materials very well just because it's so chunky, if you would excuse the expression. And then the beta particles, these guys are electrons, and electrons are pretty small. So if you have some really fast moving electrons, they can penetrate through materials. But maybe not all that much. I'm not really a fan of this picture. It doesn't really show a good difference between alpha and beta radiation. You could probably stop most alpha radiation with a few sheets of paper. Beta radiation, you would need a good sized textbook to stop pretty much all beta radiation. Gamma radiation, on the other hand, is going to be a very penetrating radiation. It's going to go through materials very, very, very well. So if you were going to rank these three in terms of least penetrating to most penetrating, this picture lays it out pretty well, but alpha radiation would be the least ability to penetrate. Beta radiation would be stronger penetrating, and gamma radiation would have the best ability to go through materials. Here's a little chart. It comes from an old textbook. This shows the effects of short-term radiation. Basically, if you get a small dose of radiation, you may not even know that you got a dose of radiation. There's a unit of measuring radiation exposure called a rem. But this says from 0 to 25 rems. You're pretty much not going to see any effects. Really, the first real thing that you would notice with radiation exposure is a decrease in white blood cell count. And you might remember from, biology class that white blood cells are the cells that will fight infection in the body. So if you get sick, then the white blood cells are the ones that tends to attack the virus and all that kind of stuff and help make you well again. So If you have a decrease in white blood cell count, then that means you might be able to get sick easier. So a decrease in white blood cell count is not really going to kill you, but the complication would be that, if you get a really strong decrease in white blood cell count, the common cold might put you under. So you got to watch out for that. And then they jump up to a humongous, dose of 500 REMS, and once you start getting into multiple hundreds of REMS, then we're talking about probable death here. Now, despite your best efforts, you're going to get some radiation exposure. Everybody does. I don't want you to be a hypochondriac, but there's naturally occurring radiation in radioactive elements in the Earth. We get radiation from the sun and from stars. There's radioactive materials all around us. But in general, the radiation exposure that we're getting from all of these things, even including some medical aspects like X-rays and things like that, really doesn't amount to a whole lot. The average person may only get less than 1 REM of exposure per year. Now, this source is about 10 years old. I imagine this is a little bit higher now, especially in the age of everybody attached to their cell phone all the time that's constantly spitting out microwaves. But so in general, we're not getting a whole lot of radiation, but we are getting some. Okay, which I'm not sure if that is the primary increase of causes of cancer, but remember, radiation is not the only cause of cancer. There are other reasons that can happen as well. All right, so that's some bad stuff. Let's get into some useful stuff. Okay, so we're talking about nuclear chemistry. What can you use nuclear chemistry for? Well, from an academic standpoint, you can use it to create new elements and help us to understand more about atomic structure and subatomic structure as we do some of these new processes where we create new elements. We can also use it to date artifacts, figure out how old a fossil is, or how old a diamond is, or if we want to date some rock and try to figure out how old is this rock, then there you go. We can also use it in the medical field in a myriad of ways. In the medical field, probably the biggest subset of uses is in imaging. We need to be able to see what's going on inside the body, and so there's a lot of medical uses with that. And then finally, we've got energy sources, and we're talking about nuclear power, right? Okay, so we can delve into each of these things a little bit more, but those are the 4 main things that nuclear chemistry is used for. So, even now, we are in the process of trying to create new elements in the periodic table. If you look at, the periodic table in most classrooms, I know the periodic table in my classroom is outdated. There's several new elements that have been created in just the last couple of years here, using a process called transmutation. Now, transmutation is accomplished one of 2 ways. Typically, it's either done with neutron bombardment or positive ion bombardment. I like the bombardment term. Basically, it means we're hitting an existing atom with a neutron. So, if you hit a uranium atom with a neutron, you think, well, wait a minute, the number of neutrons doesn't change the identity of the element. But oftentimes, what can happen is that if you create an isotope of that element that tends to go through a beta decay, then that element can actually go up in atomic number by accepting the neutron and then a subsequent beta decay. And we don't control if this happens, but oftentimes we try to make elements' atomic numbers go up by getting that element an extra neutron that ends up turning into a proton by releasing an electron. So the atomic number can actually go up there. In a positive ion bombardment, this is a more direct approach to try to make larger elements. We're actually taking alpha particles, helium nuclei, or maybe even larger nuclei like carbon or nitrogen or oxygen nuclei. And if we can get these things fast moving enough and have them hit each other, then we might be able to get them to stick and form some larger elements. Now, oftentimes we can't, get the entire positive ion. If this was a carbon nucleus, to stick to the nucleus. A lot of times some neutrons are released in the process as well, but if we got the atomic number to go up from what it was before, then that's what we're doing. You'll notice a lot of these processes start with uranium or plutonium. Uranium, by the way, is the largest naturally occurring radioactive element at element number 92. No other element past uranium is something that would exist naturally. So pretty much every element above element number 92 in the periodic table is quote unquote man-made through some sort of transmutation process. So how do they do this? Well, you've got to get these nuclei to hit each other super fast, super hard, to kind of overcome the positive repulsion that would normally push them apart. And to do that, you got to get them moving really fast. Here's a picture of a particle accelerator laboratory. This one happens to be in Illinois. And you can't really tell a whole lot from this aerial view here, but this cooling pool here, if you go underground in this facility, there are tubes in this facility that go around underneath this cooling pool, and there are really powerful electromagnets all along those tubes that can push particles around that tube really, really super fast. And so you keep pushing this particle until it gets going really, really super fast, and then once they've got one of the particles going super, super fast, then they inject another maybe the atom that they want that particle to hit into the tube, and as the particle comes around, if it collides with that atom, then they're going to get the collision that they're looking for, hopefully at the speed that they're looking for to get that process to work. A second use of nuclear chemistry is dating artifacts. We're going to come back to a little bit more about the half-life concept later. But just to go ahead and define it, half-life is defined as the amount of time required for 1/2 of a sample of radioactive atoms to decay into another element. I don't really like this picture because it shows it split right down the middle. It's a whole lot more random than that. But you can imagine, hey, I've got an original sample of atoms, and then after one half-life of time, then half of what I started with would basically turn into a different element. Now, half-lives are dependent on how stable something is. Okay, something with a really long half-life, like this radium-226, is going to be more stable. Something with a relatively short half-life, like this radium-224 is at only 3.6 days, this is going to be less stable. The idea here is, it's more radioactive, it's less stable, it's going to be releasing more radiation in less time, and in the process, more of those radium-224 atoms are going to be turning into something else much, much faster than the radium-226 atoms here. So radioactive isotopes that have shorter half-lives tend to be more dangerous, and radioactive isotopes that have longer half-lives tend to be a little bit safer. But obviously any radioactive substance is something that you want to keep an eye on. Specifically, radiocarbon dating is probably the most famous version of using a half-life to date an object. And we know that carbon-14 has a half-life of almost 6,000 years. And so if we look at the amount or percentage of carbon-14 that is in a living organism, and we compare it to, say, the carbon-14 that's in a mummy or in a fossil. We can use how much of that percentage of carbon-14 has decayed to determine how old something is. Now, radiocarbon dating is not the only kind of radio dating. It depends on what you're dating and what elements are inside it. But if you're trying to go back a whole lot longer than maybe just a few million years, then you may want to use a different isotope. So if we're dating rocks that are hundreds of millions or billions of years old, then we might choose a different isotope to focus in on to try to help us get a more accurate picture of how old that rock is or something like that. Radiocarbon dating helped us figure out that the Hope Diamond is over 600 million years old, so there you go. All right, so another use of nuclear chemistry is in the medical field. Okay, so in the medical field, you kind of subsets of uses of nuclear chemistry in the medical field. One is imaging. Okay, so imaging, we're talking about trying to see inside the body. So we can use radiation to get interior pictures of the bodies and try to figure out what's going on there. X-ray is one example of that, but we have much more powerful techniques than X-rays these days. We'll talk about some of those. Radio tracers. Okay, so this is not just like shining an X-ray through a body. A radio tracer is basically a radioactive element that's hopefully not so radioactive that it's dangerous, but it's going to replace a stable element. So if you got this molecule that is in a certain place in the body or moves around a certain way in the body, if you can take that molecule and replace an atom on that molecule with a radioactive atom, then it's easier to track where that radioactive atom goes. So radio tracers are great for tracking the flow of certain molecules in the body. We also use radiation to treat cancer. And so radiation, remember, one of the three things that can happen to a cell is that radiation exposure can either damage the cell or kill the cell. And if the cell's already been damaged and it's just growing cancer, then we could continue the radiation exposure, hopefully just on that those cancerous cells, to try to kill cells, say inside a tumor, and shrink that tumor. If we focus in on kind of the imaging aspect here, major imaging comes in the form of either an MRI, an X-ray, or a CT scan. MRI stands for medical resonance imaging. It's actually nuclear resonance imaging, but they took the nuclear off of it because nuclear scares people. Basically, this just uses very, very powerful magnets to oscillate, to vibrate nuclei, and obviously a lightweight nuclei will be able to oscillate and vibrate back and forth faster, and more heavyweight nuclei will vibrate back and forth slower, and so we can use that to get some really powerful images. So, if you need images of soft tissue, like you want to see inside somebody's brain, an X-ray can't really, do this. An X-ray is going to be able to tell you where the skull is and where the skull stops, but the X-ray through soft tissue doesn't work very well. Here's our X-ray image of a skull, and you really can't see any detail inside there. But magnetic resonance imaging can really give a whole lot of detail, even for soft tissues. And the nice thing about it is because it's just using magnets to oscillate a nuclei, and it's not actually shining any radiation through the body, and no radiation is penetrating the body. There is no effects of radiation exposure. Now, if you've ever talked to anybody who's ever had an MRI, they tell you, you got to take off all your jewelry and all that kind of stuff, and you don't want to wear earrings in the chamber because literally, that very, very super powerful magnet is going to, wreak havoc with things like that. So, I've even had people tell me that if you have tattoos with certain color ink in them, then there are metals in that ink in the tattoos that can get hot or whatever because they're oscillating so much. That may be an old wives' tale. I don't know if that's true or not. We just talked about X-rays a little bit. Now, a CT scan. this is a lot of times what people will call a CAT scan. This is a lot of radiation exposure. So you notice in these pictures, it's comparing it to days of flying. The reason they're doing that is because as you get higher up in the atmosphere on the planet, if you've got a whole lot of atmosphere to get through, then the radiation may not be getting all the way down to the ground. But if you're in an airplane, then that radiation doesn't have to pass through as much atmosphere. So you can get more radiation exposure the higher up you are. Radio tracers. All right, so radio tracers can basically track the movement of certain molecules in the body. So, there's a molecule that's really important in the thyroid gland that has iodine on it. And if you take some of those molecules out and replace that iodine with a radioactive version of iodine, maybe an iodine 131 radioactive isotope, then it'll focus on that part of the body because the thyroid gland tends to use iodine more than any other part of the body. So then you scan for the radiation that's being emitted from that iodine, and that thyroid gland may light up like a Christmas tree. If you want to track, how good is your circulation doing, or is the blood making it everywhere it needs to make it, then obviously you might use some iron. Remember, iron is in hemoglobin and red blood cells, and so if you use a radioactive version of iron and replace some of the hemoglobin and your red blood cells with that hemoglobin that has this radioactive isotope attached to it, this radio tracer attached to it, then you can see, are the blood cells making it all the way up into the capillaries and the lungs and all that kind of stuff. So there are a myriad of different isotopes that tend to focus on different parts of the body, and we can use those to track movement of molecules in the body and image where those molecules are most concentrated, and maybe where they're not. Finally, we can use radiation to treat cancers, right? If you've got a tumor in the body, maybe this is a picture of a spinal cord with a tumor on the spinal cord. If you shine, radiation on that tumor, then that could kill some of the already damaged cells in that tumor. Now, you got to be really careful with this because, this radiation can also kill and damage healthy cells, and we don't want to do that. So we've got some very specialized equipment now that can really focus in on that and hit a tumor and focus in on a tumor and only that part of the body, hopefully, so that it doesn't damage other parts. Now, if you don't have a localized cancer, if you've got some sort of lymphatic cancer that's going to be tiny tumors or spread throughout the body that you can't really use this technique for very effectively, then you may get some sort of intravenous radiation therapy where they actually put a dangerous radioactive isotope in there to try to treat that tumor. And hopefully, depending on your kind of cancer, just like for radio tracers here, certain elements tend to be focused in certain parts of the body. And so, if you've got, say, cancer in the liver, then they may use a radioactive isotope of phosphorus, and they may use a pretty high concentration of it to try to target that part of the body. All right, so that's pretty much the medical aspect of it. Now for nuclear energy, basically there's two main kinds of reactions that can happen in reactions that produce energy. We've got fusion reactions and we've got fission reactions. Now fusion is basically defined as combining small nuclei to produce larger nuclei, and it also releases a bunch of energy. That's fusion. Fusion's combining small nuclei. This is solar energy. It's what our sun is doing all day long. Our sun all day long will combine hydrogen and hydrogen to make helium, basically. Okay. Remember, hydrogen's element number 1. It makes helium. Now it can make an unstable version of helium that tends to go through a beta process, but I'm not going to get into that. On the other hand, we've got fission. This is the type of nuclear power that you would find in a nuclear power plant, or even heaven forbid a nuclear bomb or a nuclear weapon. And this basically is the opposite. And here we're combining nuclei. Here we're splitting nuclei. So in fission, we're splitting large nuclei. But small nuclei combining releases energy, and splitting large nuclei also releases energy. If we kind of focus in on nuclear fission just for a second, here's kind of a picture that shows what the reaction that happens in most nuclear power plants. The fuel rods in nuclear power plants are composed of uranium, and if we take that uranium and hit it with a neutron, we can cause it to be unstable, and then that unstable nucleus that has some extra energy may split into a couple of big chunks and maybe also some extra neutrons. And this is what we're after, right? All that extra energy that comes out of the process. And a whole lot of energy comes out of the process. How much energy? This much energy, 2.1 times 10 to the 13th joules of energy per mole. I know we don't know what a mole is quite yet in the class, but we're talking about 235 grams or so of this mercury. A mole is about the mass number in grams. And so that amount of energy is quite a bit. If you start comparing it to burning something like natural gas, methane, you get about 26 million times the energy per mole of fuel. So we're talking, this is a reason why nuclear submarines, like to use a nuclear reactor as opposed to, a combustion engine to get that submarine to move around, because the thing can, for the same amount of, basically the same amount of particles of fuel, you're getting so much more energy that nuclear submarine can drive around the globe a whole lot of times without refilling up. Now, a chain reaction can happen with nuclear fission. You can imagine, these extra neutrons that are coming off of here. If those extra neutrons were to hit another uranium atom and cause that atom to split, then the reaction would essentially be self-sustaining. And if the nuclear reaction has atoms that are packed close enough together so that just about every neutron is going to come off and hit another radioactive atom and split it, then you can get a chain reaction. One nucleus splitting turns into 2, turns into 4, turns into more, and you get this exponential growth. Here's where we get an explosion. Okay, so this is the kind of thing that you would see in a nuclear bomb like the one that happened at Nagasaki or Hiroshima. Nuclear fusion. All right, now if we take a look at fusion compared to fission, remember fusion is combining nuclei. Now, this produces more energy than fission per mole of particles that are in the reaction. But the problem with trying to use fusion is that it only happens at I'm going to say very, because one very is not enough, high temperature and high pressure, okay? And so that's what's happening in the sun. The sun has so much gravity that it can cram those hydrogen atoms really close together so that they're all at really super high pressure. And because this is releasing a whole lot of energy, you've got a high temperature. To get a fission reaction started requires so much energy or to get a fusion reaction started requires so much energy that just the temperature is so ridiculous. Also, because of this super high temperature and super high pressure, if you tried to build a reactor to house this nuclear fusion reaction, then there's not a whole lot of materials that you could build that thing out of that would be able to withstand those temperatures and those pressures. So literally, even if we could get the reaction going, which right now we really can't, how are you going to house the reaction so that you can harness the energy from it safely? That's not something that we're really able to do right now. Okay? All right, so that's going to conclude today's lesson on radiation and the effects of radiation and practical applications of nuclear chemistry, as well as nuclear fission and nuclear fusion.